So in this video, I will walk you through my solution for the M3 practice hackathon, where the goal was to develop a reliable regressor to predict medical insurance charges. I implemented the solution using Python in Google Colab environment, leveraging libraries like Pandas and Seaborn. So first of all, you can see here, I imported the pandas, load the training and test data set, and verify the columns. And the second part is data loading and cleaning. So I loaded and inspect the data. I worked with two data sets, the training data and the testing data. Upon inspection, I immediately noticed a discrepancy. So the training data used string labels for categorical variables like sex, smoker, and region, whereas the test data provided by the competition used integer encodings. So to ensure consistency, I created a mapping dictionary based on the data dictionary provided in the PDF. And I mapped the string values in the training set to their corresponding integers. This was a crucial first step to ensure my model could actually process the test data later. I also performed a data quality check and found one duplicate row in the training set, which I removed to prevent any bias in the model. So you can see in this part, I first loaded the two data sets and then created the mapping dictionary, apply it to the training data set, checked and removed the duplicate row, and also finally displayed it to verify. So here's the result. And the next part is EDA. So before modeling, I performed the exploratory data analysis to understand the data. I visualized the distribution of the target variable charges and looked at correlations. The most significant finding was from the box plots and scatter plots, which showed a very strong relationship between smoking status and charges. Smokers consistently had much higher medical costs than non-smokers. This insight confirmed that smokers would be a critical feature for any model to capture. So you can see from here, I first I figured out the distribution of charges and then uh, did a correlation heat map and found the relationship between BMI and charges and the box plots and also the relationship between smoker and charges and finally the region and charges. So this is the first diagram and here is the correlation matrix and BMI and charges and finally charges by smoking status and charges by region. And next part is feature engineering and data splitting. So for feature engineering, I set up a robust pre-processing pipeline using a scikit-learn's calling transformer. So for numerical features, I applied standard scalar to features like age, BMI, and children to normalize their scales, which you can see from here. And for categorical features, I applied one hot encoder to sex, smoker, and region. So even though they were already integer encoded, treating them as nominal categories ensures the model does not assume a mathematical order where it should not exist. I then split the processed training data into a 80% of training set and a 20% of validation set to stimulate how the model would perform on unseen data, which you can see from here. And the next step is model training. And now we can just use this part to address the first discussion prompt, which is what did I do to improve the performance of my regressor? So my primary strategy was model selection and comparison. I didn't just stick to a simple linear regression. I trained and evaluated three different algorithms, which is first linear regression as a baseline, and also random forest regressor, and also XGBoost regressor. So by comparing their performance on the validation set, I found that the random forest regressor significantly outperformed the others, achieving the lowest root mean squared error of approximately 4,672. So the linear regression model, by comparison, had a much higher RMSE of nearly 6,000, which you can see from here, the result. And choosing a nonlinear model like random forest was the key because it could capture complex interactions in the data, such as the specific jump in cost for smokers with high BMI that a simple linear model might miss. And the next part, also here, I can also answer the second prompt, which is what did I do to assess and improve the fit of my regressor? So to assess the fit, I used matrix validation and cross validation. So I looked first for the metrics, I looked at both RMSE and R squared scores. So my final random forest model achieved an R squared of roughly 88%, which you can see from here, right here, and which suggests a very good fit. And second, for cross validation, to ensure the model was not just overfitting to my specific validation split, I performed five-fold cross validation on the entire training dataset. So the mean RMSE across the five folds was approximately 4,827, which is here. So which was very consistent with my single validation score. This confirmed that the model is robust and generalizes well to different subsets of the data. And finally, I did the final part. In conclusion, so finally, I retrained the best model, the random forest, on the full training dataset to maximize the information I could learn from. I then generated predictions for the testing data file and saved them to the submitting file for the Kaggle submission. Summarize by fixing schema inconsistencies, choosing a powerful nonlinear model, and rigorously validating it with cross-validation, I was able to build a reliable regressor for this task. Thank you for watching. And here is the final part of my coding, which I finally saved the file and then uploaded it. Thank you.